Hello, everyone. Welcome back. So starting from today, for the next couple of hours, we are going to talk about the linear programming duality or LP duality. Okay, and in general, the duality theory addresses itself to the research of the connection between two very closely related linear programming problems, and one is the primary LP, and the another is the dual LP. Okay, and the dual problem can be directly defined from the original LP, which is the primary LP models, right? And these two problems are closely related each other, so that the optimal solution of one problem automatically provides the optimal solution to the other problems. Okay, and if that is not the case, at least if the primary LP is the maximization problem, then the dual can be used to find the upper bounds on its optimal objective function value. Okay, and of course, similarly, if the primer is the minimization problem, then the dual gives the lower bounds on the optimal objective function value. Okay, and I will show you this with the chair and table production example problem in a minute. But I've got to tell you that this is very useful, okay, especially in certifying the optimality of a candidate solution to the primary LP problems. Okay. Okay, so first let me share my screen. Okay, here's slides, right? Okay. Okay, so let's revisit the chair and table production example problem that we discussed earlier this semester. So just remind you that in this example, each table needs the two large bricks and two small bricks, right? So see here, each table, this is the table that does need two large bricks and two small bricks here, right? And each chair, so this is the chair. So each chair needs one large brick, right? And two small bricks, okay? However, we have only the 6 large bricks and 8 small bricks, right? And we wish to maximize the profit. So profits of the producing the these chairs and tables, right? And well, I didn't include the formulation here, but since this is a very simple and easy, so let's do that. So in this example, you have to decide how many tables and chairs to be produced, right? So let's define X1 stands for the number of tables produced, and X2 is the number of chairs produced. Okay, so that's our decision variable. And if I say G, capital G, is the total profit, then of course we'd like to maximize the total profit, right? So G would be using the real values, 16 and 10 here. It's going to be 16 times x1 plus 10 times x2, right? And what constraint do we need? The resource constraint, right? For large bricks and small bricks. So we do need two constraints, right? And two large bricks are needed for making one table, right? And also one large brick is required for making a chair, but only 6 large bricks available, right? So this translates to, so subject to 2x1 plus x2 is less than equal to 6, right? That's for the large brick. Likewise, for the small bricks, we are going to have 2x1 plus 2x2 less than equal to 8, right? For small bricks. And the production rate cannot be negative. So of course you need to add non-negativity restrictions for both x1 and x2 variable. So I believe that's what we've done last time, right? Okay. So then let's say, so let's say this is the primer LP, okay? Now I'm going to split the screen in half. So, okay, cool. Okay, and then I'm gonna choose Microsoft Word. Okay, with this. Okay, great. Thanks, Dominic, for these useful tips. I've learned it from him last time. So he posted the comments on my YouTube video, and looks great. Thank you. Okay, so I'm gonna write down. So let me disable my video and this cursor. Okay, right here. Okay, so now I'm gonna increase the view a little bit. So let me zoom in. A little bit more. Okay. Okay, so I said this original optimization LP is the primary LP. So, and now let's think about how we should begin to approach this problem analytically. Okay, and let's not use the graphical method at the moment. Okay, then how could solve this problem? So the first thing is definitely we want to maximize this value, right? Maximize 16x1 plus 10x2, our objective function, right? So first thing is first. So we want to maximize G equals 16x1 plus 10x2, right? Okay, sorry. Okay. And what else? And we do have non-negativity restrictions, right? So both x1 and x2 are greater than equal to 0, right? So at the moment, let's just consider this, okay? Then without considering these two constraints, the maximum value this objective can achieve would be plus infinite. Is that right? So as of now, without considering these two constraints, we can say that this plus infinite is an upper bound to the maximum value of our objective function g can take. Is that right? So I'd say this is going to be actually greater than equal to our current objective function, right? So that's going to be our upper bound on the optimal value of our current objective function. Okay. However, we have these two constraints, right? They need to be considered, right? So let's take care of them just one by one. Of course, intuitively, we can imagine that our current upper bound of infinite will be minimized, will be reduced if we consider these constraints, right? So first, you notice, let's consider the second constraint first, okay? So which is this second constraint. So we have 2x1 plus 2x2 is less than equal to 8. Now, what we're going to do is we multiply this constraint on both sides by 8. Okay, so multiply by 8. We're going to have 16x1 plus 16x2 less than equal to 64. Is that right? And the point is, if the coefficient of these two variables, which is 16, right, each, if these two values are greater than or equal to the coefficients of the corresponding variables in our objective function, which are 16 and 10, then the right-hand side value, which is 64, acts as an upper bound on the optimal value of our objective function. Is that correct? So as of now, this value 64 is going to be our new upper bound, right? So that's going to be our new upper bound, right? And of course, because this is that's because this is greater than equal to our current objective function value, which is g, right? And g is equal to 16x1 plus 10x2, right? So it's a big improvement from the previous upper bound, which is infinite, and right now 64. So infinite to 64 is a big improvement, right? And can we do better? Of course. So as of now, let's look at the first constraint, which is 2x1 plus x2 is less than equal to 6. Okay. So let me write down here 2x1 plus x2 is less than equals 6. Now, what I'm going to do is multiply both sides by 10. Okay. Then we're gonna come up with 20x1 plus 10x2 less than equals 60. Is that right? So of course, the coefficient of x1, which is 20, this is greater than the coefficient of x1 in our objective, which is 16, right? Also, the coefficient of x2, which is 10, is at least the same as the one in our objective. So the right-hand side value of 60 becomes our new upper bound, right? Because this is still greater than equal to our objective function value, which is g, is equal to this, right? Of course, this value 60 is smaller than 64, lower than 64 as an upper bound, right? So in general, it's better because it's tighter upper bound, right? 60 is tighter upper bound to our chair and table problems, right? Which is maximizing the objective function, right? Okay, now we can do even better job. So this time, let's use both of these two constraints, constraint number 1 and 2 at once, okay? So what you're going to do is to multiply the first constraint by 6. Okay, so let me write it down here. So here, multiply by 6. Our first constraint, 2x1 plus x2, less than equal to 6 times 6, right? And then also multiply 2, second constraint by 2. So 2 times our second constraint, 2x1 plus 2x2, less than equal to 2 times 8. Okay. And then we are going to add this. Okay. Then what do we have? It's going to be 6 times 2, 12x1 plus 2 times 2, 4x1. So we are going to have 16x1. And then 6 times 1 plus 2 times 2. So it's going to be 10x2, right? How about the right-hand side? It's going to be 36 in 16. So that's going to be 52. Is that right? Okay. So we finally been able to get the optimal objective function value, actually, in this case, right? So which is 52. And we notice that this left-hand side is identical to our current objective function, right? So that's exactly same as our objective function, right? Which is 16x1 plus 10x2. Is that correct? So, by the way, did you notice while we are solving this table and chair maximization problem, we actually used the minimization approach to solve this maximization problem, right? So starting from plus infinite, we got 64, and then 60, and finally we have 52, right? And this minimization problem we solved is what he called the dual to the maximization primer LP problems. Okay. So now let's put this idea together in a mathematical framework. So now I'm going to talk about the dual problem, okay? Dual LP versus this primer LP. Okay. I think I did something wrong. Okay. It's fine. So let's suppose to obtain the tightest upper bound to the maximum, you want to multiply the constraints, right? These two constraints by non-negative numbers, like we did earlier here, okay? We multiply by 8, we multiply by 10, and then here we multiply by 6 and 2, right? So we want to multiply constraint by non-negative numbers. So let's use y1 and y2, okay? And these non-negative numbers are like this, right? So both y1 and y2 are greater than equal to, right? And let's say that the first constraint by y1, okay? So in our case, the y1 value is equal to 6, right? And the second constraint by y2. So in our case, the y2 value is actually 2, equals 2, right? So here, the first constraint is 2x1 plus x2. But we are going to multiply by y1, right? also to the right-hand side, it's going to be 6y1, right? Likewise, for the second constraint, we are going to multiply by y2. So 2x1 plus 2x2, right? And then 8 times y2, right? And then add them. And then take out x1. So it's going to be 2y1 plus 2y2, right? 2y1 plus 2y2 x1 plus for x2 term, it's going to be y1 plus 2y2, right? y1 plus 2y2 x2 is less than equals what? 6y1 plus 8y2. Is that correct? So now the coefficients for x1 and x2 in this new inequality constraint. So I'm talking about these coefficient values and these coefficient values. And also our original objective function value. If you look at that, the coefficient for x1 is 16. Coefficient for x2 variable is 10, right? So this value has to be compared to 16, and this value has to be compared to 10 to justify that the right-hand side value will give the upper bound on our objective function. So eventually, we compare these this expression with our objective function, right? So as we did earlier, we have to make sure that the corresponding coefficient of x1 and x2 must be greater than or equal to the coefficient of x1 and x2 in our objective function, right? So what you need is this 2y1 plus 2y2 has to be greater than equal to 16, right? Also, this coefficient value, y1 plus 2y2 are greater than equal to 10 here. Is that right? If these are satisfied, then the right-hand side value, which is this, becomes the upper bound to the maximum value the objective function can take, right? So our goal is to minimize this upper bound value, okay? So our goal is going to be minimize 6y1 plus 8y2, okay? And subject to these two constraints, okay? With the non-negativity restriction. So I'm going to put them in here, y1 and y2 has to be greater than equal to 0. So actually, this is the dual LP. Given this is the primal LP. Okay. So from this example, what I could tell you is that a dual of the maximization problem can be thought of as trying to minimize the upper bound, right? This upper bound. Minimize the upper bound from infinite, right? From infinite to the maximum, which is 52 in our case, right? Which becomes definitely the minimization problem. Of course, for a minimization primer problem, the dual is going to be the maximizing the lower bound to achieve the tight lower bounds, right? Okay, so with keeping this in mind, now let's talk about the primer dual relationship in linear programming using a symmetric primer dual pair, which can be found in most textbooks. Okay. So let's go back to our PowerPoint slide. I think this is the one, right? Okay. Okay. So the first thing, just to let you know, this symmetric primer dual pair has some characteristics such that if the primer LP is, so this is the primer LP problem, right? So this is the primer LP. If this primer LP is n by n, which means there are m different constraints, and it's not including the non-negativity instruction, non-negativity restriction, and n different variables. Okay, then the dual LP. So the dual LP is this side. Okay. So this is the dual LP. Then the dual LP is going to be n by m. Okay. So in dual LP, there's going to be n different constraints, not including the non-negativity, and m different variables. Okay. Okay, so actually this is more condensed representation of this. Okay, so using the algebra and the matrix notation. Okay. So this is the primer problem. This is the dual problem. Okay. And the primer problem, so in this case, is a minimization problem with greater than equal constraint. Okay. While the dual problem, in this case, is the maximization problem with less than equal constraint. Okay. And of course, here, that's the transpose of the matrix A, okay? Instead of original matrix A. And what other thing? For every variable in the primal problem, there is a corresponding inequality constraints, okay, in the dual problem. Likewise, for every inequality constraint, not including the non-negativity, there is a corresponding dual variables, okay? And the right-hand side vector, B, of the primal problem serves as the objective coefficient, okay, of the dual problem. And the objective coefficient in the primal problem serves as the right-hand side values of the dual problem. Interesting, right? Okay, now let's take a simple example. So here, the primal problem is the minimization with greater than equal constraint, right? While the dual problem is the maximization with less than equal constraint, okay? And like I said earlier, the objective coefficient of the primal problem serves as the right-hand side values of the dual problem in order, right? 2010. And conversely, the right-hand side value of the primal problem serves as the objective coefficient of the dual problem, okay? And to every constraint in the primal, there corresponds a dual variable, okay? Which means if you have two constraints in the primal problem, then there should be two decision variables in dual problem, okay? Likewise, to every variable in the primal problem, there corresponds a constraint in the dual problem, okay? That is, if you have two decision variables in the primal problem, then there should be two constraints in the dual problem. And of course, both primal and dual problems include sign restrictions of the decision variables. Okay, now let's consider let's suppose we have an inequality reversed in the primal problem. Then how do we write the dual of this problem? So you remember in the symmetrical primal dual pair, the minimization problem has greater than equal constraint, right? And the non-negativity variable. But as it shows in this screen, what if one of the constraints has reversed the sign here? Then how could we construct the dual of this problem? So in this case, first, we need to transform the problem. So we multiply the offending inequality by -1, okay? So reversing the direction of the inequality can be performed right here. So now the problem is in the form of the primer, the symmetric primer dual pair, which is minimization problem with or greater than equal sign, right? So now we can write this dual problem like this. So in the dual problem, we have maximization with or less than equal constraint. And objective coefficient 2010 becomes the right-hand side value in order. And the right-hand side values, -6, 8, becomes the objective coefficient values. And here, the constraint matrix, constraint coefficient matrix is -5, -1, 2, 2. Right? That's the matrix A. Then here, we are going to have A transpose matrix. So that's going to be -5, 2, -1, 2. That's why we have -5, 2, -1, 2, right? Okay, now it's interesting to make a change a variable. So let's set y1 prime is equal to -y1. Then it's the same as dual of the symmetric primal dual pair, except for non-positivity here, replacing non-negativity. You remember in the symmetric primal dual pair, maximization problem has less than equal constraint and non-negativity variables, right? Now I replace y1. No, y1 prime with y1. Okay. Then the original problem, I mean the primal problem is this, right? So we can notice that the reverse direction of the constraint in the primal problem corresponds to the reverse direction of the variable in the dual problem. Okay. Now, okay. Now let's consider another variation. In the symmetric primal dual pair, minimization problem has greater than equal sign, greater than or equal constraint, and the non-negativity variables. Now let's suppose rather than an inequality constraint, we have a equality constraint. In this case, how do we write the dual of this problem? So first, we need to transform the equality constraint into the equality, so we need to transform the equality constraint into the equivalent inequalities, right? And then we multiply, again, the offending inequality by -1. So actually, we have reverse direction, right? So our problem in the form of the primal problem in the symmetric primal dual pair is just like this. Now we can write this dual problem right? So just to let you know, here we've chosen to name our dual variables, not y1, y2, y3, but y1 prime and y1 double prime and y2, because the first two constraints in the primer problems come from only one equality constraint, okay? So that's why we decide to name this y1 prime and y1 double prime, okay? Okay, also notice that the pair of the dual variables, y1 prime and y1 double prime, always appear with opposite signs, right? So here, as you can see here, there's always opposite signs. Now, let's substitute y1 for y1 prime minus y1 double prime, okay? Then we note that we cannot include the constraint on the sign of y1, right? Because the y1 variable is the difference of two variables. So the value of y1 could be negative, 0, or positive, right? So that's why we didn't include any constraint on the sign of y1 variable here. So this is the same as the dual in the symmetric primal dual pair, right? Except for the missing non-negativity restriction. So we can say that the dual problem looks like that, right? So the equality of the constraint in the primal problem corresponds to the, here URS stands for unrestricted insight, okay? So the equality of the constraint in the primal problem corresponds to the unrestricted insight of the variable, the dual problem. Actually, in the maximization problem. Okay. Okay, now I'm going to show you the dual of the dual problem. The symmetric primal dual pair becomes the primal problem, okay? So first, let's think about how we could write the dual of the dual problem, okay? Let's take the dual of this problem. So first, we must write it as a minimization problem with greater than equal constraint. So in this case, this problem D is equivalent to problem D prime. You know, minimizing the negative of a function, here's the same solution, except for the sign, as the maximizing the functions, right? So also negating both sides of a less than equal constraint produces a greater than equal constraint. Is that right? So what I did is just multiply negative 1 on both sides to here. And then you come up with this new constraint, right? Okay, So the dual of the problem D prime is problem D double prime, right? In this case. And the objective coefficient of the primer serves as the right-hand side of the dual problem. And the right-hand side of the primer serves as the objective coefficient of the dual, right? So this is correct. Now problem, the D double prime is equivalent to problem P, the primer problem. Because again, the maximizing the negative of a function is the same solution as minimizing the function, except for signs, right? And also negating the both sides of a less than equal constraint produces a greater than equal constraint, right? So we can conclude that given the primal dual pair of LP problems, it is truly arbitrary, which is referred to as the primer and which is referred to as a dual, okay? Okay, the dual of an LP may be found by first rewriting the LP in the form of one of the LPs in the symmetric primal dual pair. And on the other hand, the dual can be written directly for any LP using these relationships, okay? So I've been using this conversion table frequently. So please keep this in handy, okay? And I'm gonna show you how to use this conversion table in a minute. Okay, now, given this primer LP problem, the maximization problem, how do you write the dual problem? This is very easy because the given primer problem is the maximization problem in the symmetrical problem, symmetrical primal dual pair, which is maximization with all less than equal constraint and non-negativity restriction. So the dual must be the minimization problem. Let me write it down here. Minimization problem with all greater than equal sign, okay? And also non-negativity restrictions, okay? So if I use y variable as a dual variable, then I'm gonna write down y1, y2, y3, right? How do you know we have three dual variables? Because there are three primary constraints, right? So we must have three dual variables, okay? And in the primary system, we have only two decision variables, right? Which implies that in the dual system, we are going to have only two constraints, okay? And so I'm gonna just write it down, y1, y2, y3, 2 times. And actually, I'm gonna write down one more time because we do need sign restrictions for every dual variables, right? And here, the constraint coefficient matrix, A matrix is 1, 0, 0, 2, 3, 2. A transpose matrix would be 1, 0, 3, and 0, 2, 2, right? So that's going to be the constraint coefficient in our dual problem. Okay, so it's going to be 1, 0, 3, and 0, 2, 2, right? And objective coefficients 3 and 5 becomes the right-hand side values in order. Likewise, 4, 12, 18. The right-hand side values becomes the objective coefficient values in order. So this is going to be our dual LP. Okay. Okay, next example is also very easy. Because the given LP is the minimization problem with all greater than equal sign and non-negativity restriction. So dual LP must be the maximization problem with all less than equal constraint, and also each decision variable has non-negativity restrictions. Okay. This time, the primary LP is 3 by 2. So dual LP must be 2 by 3, like before. Okay. Again, let's use y variable as a dual variable. y1, y2, y3, y1, y2, y3. Then y1, y2, and y3. All of the dual variable must have non-negativity restriction. And then objective coefficient value, 1, -1 becomes the right-hand side value. 4, 1, 3 becomes the objective coefficient. And the constraint coefficient matrix, which is 2, 1, 1, 1, 1, 2, becomes the A transpose matrix, 2, 1, 1, 1, 1, 2, right? So 2, 1, 1, 1, 1, 2. Very easy. This is our dual LP, given this as a primal LP. Okay. Okay. Now, this is the given primal problem. Then how do you write the dual LP? So this is not the maximization problem, the symmetrical primal dual pair, right? Because as you can see here, some constraint have as the greater than equal sign, and we have one equality constraint, and two decision variables has no sign restrictions, right? So in this case, we are going to use the conversion table. So I'm gonna split the screen in half. Okay. And then zoom out. Oh. Just a little bit. Okay, like this. Okay. And then I'm going to have new screen, no, new page. Here. Oh, and okay, I'm gonna copy this. And paste here. Okay. Let me is the okay font size. Let me see if I can. Oh, I cannot do that. Okay, so let me. Need to maximize the screen usage. Okay, I think this is should be okay. Okay, this is better. Okay, now I'm going to bring back the conversion table. This one, right? This way. Okay, okay. It's much better. Okay, now I'm going to show you how to use this conversion table. But first, because the given primer LP is the maximization problem, so our dual LP is going to be the minimization problem, right? So I'm going to put minimization here. And here, the given LP, we have 1, 2, 3, 4 different constraints. But we have 3 different primary variables. It's going to be 4 by 3 system. So our dual must be 3 by 4, which means we are going to have 3 different constraints and 4 different dual variables. Okay. So again, let's use y variable. Then we are going to have y1, y2, y3, and y4. Okay. And I'm going to write it down 3 times more. y1, y2, y3, y4, y1, y2, y3, and y4. Okay. And let's write it down one more time because we do need sign restriction for each dual variable, right? Okay. And the first thing, because the objective coefficient in the primary problem is 4, -1, 2, we're going to have right-hand side values 4, -1, 2 in order, right? And the right-hand side values of the primary problem is 5, 7, 6, 4. So we are going to have 5, 7, 6, 4 as the objective coefficient, right? And the constraint coefficient matrix A is going to be 1, 2, 0, 2, 1, 0, 0, 2, 1, and 1, 0, 1. Is that right? Let me double check. 1, 2, 0, 2, 1, 0, 0, 2, 1, and 1, 0, 1, right? Okay, which means the constraint coefficient in the dual problems is going to be A transpose matrix. That's going to be 1, 2, 0, 1, 2, 1, 2, 0, 0, 0, 1, 1, right? So we are going to have 1, 2, 0, 1, and 2, 1, 2, 0. And we have 0, 0, 1, 1. Okay. Oh, sorry, I didn't mean to. Okay, now it's time to use this conversion table. So in order to do that, because the given LP, is the maximization problem, right? So we need to start from this side, maximization problem. Okay. So here, in the maximization problem, the first constraint has less than equal sign, right? And also second constraint has less than equal sign. So I'm going to write down here, in the maximization problem, the first and second constraint has less than equal sign, right? Just like this. And this implies that in the minimization problem, the first and second variable has greater than equal sign, okay? So in the minimization problem, we know that first and second dual variable has greater than equal sign, okay? Okay, and in the maximization problem, we know that the third constraint has greater than equal sign, right? So in the maximization problem, third constraint has greater than equal sign. This implies that in the minimization problem, the third decision variable has less than equal sign, okay, like this. So similarly, the fourth constraint in the maximization problem has equal sign, right? So here, the fourth constraint in the maximization problem has equality constraint. This implies that in the minimization problem, the fourth decision variable has no restrictions. So here, Y4 has unrestricted in sign, URS, okay? Now we need to determine the sign of each constraint. In order to do that, we need to look at sign restriction on the primer, which is the maximization problem, okay? So in the maximization problem, the first decision variable has greater than equal sign, right? So this time we need to look at this side, right? The maximization problem, the first decision variable has greater than equal sign, right? So first decision variable has greater than equal sign. This implies that in the minimization problem, the first constraint must have greater than equal sign, okay? And here in the maximization problem, two other variables has no sign restriction. So in the maximization problem, two other variables, second and third variable has no sign restriction. This implies that second and third constraint, the minimization problem, must be equation. So we're going to have equal sign there. Okay. So this is the dual LP given primary LP like that. And this is how we could use this conversion table. Okay. That's very easy. Okay, so this is all for today. And next time, I'm going to continue to talk about LP duality. Okay. Thank you, everyone.